Let's graph an inequality like this. The first thing I would like for you to notice is that this is a linear inequality. So it's in the shape and form of a linear equation, but it just doesn't have an equal sign. So it's not an equation, it's an inequality. But we are going to put it in slope-intercept form. So think about slope-intercept form like this, y equals mx plus b. So we want to put this in this form so that we can graph the y-intercept and then we can follow the directions in the slope. So we're going to treat it very much like a linear equation, but it's a linear inequality. So the line's going to still be in the same place that it would be if it were an equals problem, but we will be shading either up or down, and we'll see how to discern that in just a minute. The other thing that's different about this is we will have either a dotted line or a solid line, and we'll talk about how you make that determination here in just a minute. But the first thing I want to do is to get this in this form. So let me recopy this. So there you go. This is what I have. So you'll notice that the x on this is on the right side of the equal sign, but our x is on the left side of this symbol. So we need to get this over there. So the mathematical way to do that is to add 3x to both sides. And that's going to cause those to cancel. Now you'll notice that over here I could have written 10 plus 3x, but I didn't. And the reason I didn't is notice that it's y equals mx plus b. In other words, the x comes right after the equal sign, so that's why I called it 3x plus 10 and not 10 plus 3x. I want the x to be right next to that. So that's the first step, adding 3x to both sides. Sometimes I shorten that up by thinking of moving this from one side to the other. And when you move a term like negative 3x over to the other side, it changes sign, so it becomes 3x. So sometimes I do that just to speed things up. You can too, but I do think early on it's good to think about inverse operations. The inverse operation of a negative 3x is to add positive 3x to both sides, so you end up with this. And then, of course, the next step is to remove this multiplication by negative 5. Well, you do that by dividing both sides by negative 5. Of course, these are going to cancel. I get y. For right now, I'm going to reverse this. I'll explain why in just a minute. And then look at what I have. I have 3 divided by negative 5. I'm going to call that negative 3/5 x. The negative goes with the top number. So it's negative 3/5 x. And then I have 10 divided by negative 5, which is negative 2. So this is my slope-intercept form of this original equation that I had up here, or inequality that I had up here. Okay, so why did I reverse the direction of this? So there's a rule in mathematics that says if you multiply or divide both sides of an inequality, something that's not equal, it's less than, greater than, less than or equal, or greater than or equal. If you multiply or divide both sides by a negative number, you have to reverse the direction of the inequality. So since we divided both sides by a negative 5, I had to reverse this to greater than. So this is what I'm going to be graphing here in just a minute, that. And the way I would graph this, let me write it right here. There's a couple different ways to do this. What I would do is graph this in slope-intercept form. So I've got a y-intercept of negative 2. I'm going to plot that. So there's my negative 2. And then I'm going to go down 3 and to the right 5. So down 3, 1, 2, 3, 1, 2, 3, 4, 5. You notice I'm trying to keep my spacing just right. So I've got this dot. Now, if you have greater than or less than, it's going to be a dotted line. So this one's going to be a dotted line. I'm not going to draw a solid line through this. If you have equals, greater than or equals, or less than or equals, then you draw a solid line. But this is greater than, so it's going to be a dotted line. And I want you to notice the line looks something like that. So I have a dotted line, and now because it's greater than, I'm going to put my pen on the line, and it's greater than, so I'm going to shade up, so up from the line. So what this means, I'm shading. I either needed to shade above or below the line. Since it was greater than, I shaded above. What this shading means is it means any point that landed over here, any point over here, any ordered pair here, any XY ordered pair over here, if I were to substitute it in here, it would make a true statement. And anything not in the shaded region, anything below here, or on a dotted line, would not be a solution. So that's the importance of a dotted line or a solid line. In mathematics, a solid line means that any point that falls on the line is a solution. It's part of the solution set. But when you have a dotted line, anything that falls on the line is not a solution. So this shaded region represents all of the ordered pairs that if you were to put in the X value and put in the Y value, it would result in a true statement. So let me show you what I'm talking about. So let's just pick a random point that's over here. Like for example, notice that 0, 0 is very clearly in the shaded region. So 0, 0. Well, think about, this is X and that's Y. So think about 0, 0. You have an X and a Y value. If you put this 0 in X's place, of course, -3/5 times 0 is 0. And then you put this 0 there, what you would have is 0 is greater than -2. Do you understand that? So if I put 0 there, -3/5 times 0 is 0. 0 minus 2 is -2. So I get -2 over there. And I put 0 in Y's place. I get 0 is greater than -2. Well, is 0 greater than -2? Yes. So notice it's in the shaded region. So that's what we mean by saying any point in the shaded region would be a true statement and therefore is a solution. So notice there's a bunch of answers to this that work, and then there's a bunch of answers down here that would not work. So this is by doing a test point. Now some people do their shading that way. Instead of looking at this and saying greater than and getting on the line and going up, what they do is they do a test point. So I could have, before I did the shading, I could have tested this point. Since it's true, I would have known, well, that point is above the line, so I'll shade above the line. Some people do the shading that way. You can do that. I don't prefer it, but you can do that. You can do a test point. So if the test point proves true, you shade that way. If the test point is false, then you shade the other way. So if I had checked a test point down here and I plugged it in, it would have been false. Therefore, I would have known, hey, you got to shade the other direction. So it's either going to be above the line or below the line. In this case, it was above the line because it was greater than, but it's also above the line because 0, 0 is above the line, and it was true. So I shaded above the line for that reason as well. Anyway, so this is how you graph a linear inequality. So a linear inequality. See you later.